begin our discussion on organic reactions and thermodynamics in this series of lectures in the next few weeks. Before I go to the next section of our lectures, I want to say a few words that mostly students encounter while we are going deep into different reactions of organic chemistry. That it's mainly because they didn't have enough background to study organic reactions. So, as we have already done from lectures 1 to lectures 15, we have covered very important organic chemistry concepts. So, as you go along to discover more or study more organic reactions, it's very important for you to study the previous most important organic chemistry concepts. So we started in lecture 1 by studying structure and bonding, which mainly has hybridizations, resonance structures, drawing different resonance structures, and identifying the hybridization of carbons. In the next section, we studied acids and bases. So the concept or the definition of acids and bases when it comes to organic chemistry is a very important concept, because most of the organic reactions involve a concept of acidity and basicity, strengths of an acid and strengths of a base, and understanding what conjugate base or conjugate acid would be formed as a result of a certain forward or backward reaction. So it's really important to review acids and bases as it comes to organic chemistry. Very important, in the third chapter or in the previous lecture series, we have seen functional groups. Functional groups are very important to understand the numerous types of organic reactions that we'll be discussing. So when you see different molecules, different organic compounds, very complex organic compounds, you might be overwhelmed, but you shouldn't be overwhelmed. As long as you understood what functional group is contained in that particular organic compound, the reaction it can undergo, the reaction or the transformation it can undergo is very limited. So please understand the few organic functional groups, such as alcohols, alkenes, alkyl chlorides, aldehydes, ketones. If you know simply these functional groups, you don't have to know all the numerous millions, trillions of organic compounds, because they fall under one of these or a combination of these functional groups. The reaction is also, the one we'll be studying, is limited also. So numerous, many compounds you see, no matter how complex they are very easy. So understand functional groups. What is the functional group that's responsible for certain reactivity? And I encourage you to review back again in my previous lecture, functional groups. The fourth is to just understand how we name compounds. That was demonstrated by a chapter or a section in alkanes. Understand cycloalkanes. So in cycloalkanes, conformation; in alkanes, Newman projections, rotations, free rotations, and all that. That would help you how fast a certain alkane could react, or what is the stability of a certain cycloalkane is. Very important section we just finished was stereochemistry. Remember how to assign R and A's, relationships between chemical compounds as far as is constitutional isomerism or stereochemical isomerism, which is stereoisomers like diastereomers, enantiomers, mesocompounds, plane of symmetry, polarimetry. These are also fundamental concepts you need to understand. So in the next few lectures, we'll focus on organic reactions in thermodynamics. This is just a transition to a more application of all of what we have studied before. So the fundamental ones are in lecture series 1 to 15. Please review back again all the videos. They have also solved problems I did on the videos. So please review the sections from 1 to 15. So as we proceed to organic reactions in thermodynamics, the reason why we would be obviously be interested in organic reaction is that's the main point of organic chemistry. As you know, all pharmaceuticals, that means medicines, starting from any painkiller to anti-cancer drugs, they are a result of a chemical reaction. Foods we consume have undergone some type of chemical reaction in the production of food. Enzymes, enzymology in our bodies or in plants or wherever, biological systems use enzymes to catalyze reactions. These are organic reactions, actually. A complex organic transformation involves enzymes. How about DNA to protein synthesis? All of the proteins that are being synthesized in our body every second, every microsecond, involve a chemical reaction catalyzed by enzymes. Those are the instruction by DNA to produce a certain type of protein involves myriads of chemical reactions. Photosynthesis. Obviously, we don't synthesize our food, but plants do synthesize food. They use a process or a particular light-activated reaction called photosynthesis to convert carbon dioxide to glucose. And how we also produce energy in our bodies. Our cells produce ATP from glycolysis, from undergoing glucose oxidation and reduction and so on. Those are organic reactions. So even though there are so many types of transformations that can be done, the organic reactions are very few to study and very few to understand. Together with any chemical reaction, there is energy associated with it. That means how stable that product is formed, how fast that reaction could go as a kinetic. Studies would involve energetics of the chemical reaction. That's why I have a title as organic reactions and the thermodynamics associated with it. So this is just a background to give you what we'll be looking at. So in the next few lectures we'll be studying in general organic reactions, but in the next chapter we'll also pick one particular kind of functional group and demonstrate different type of organic reactions. Continuing our discussion on organic reactions, at least in broader sense, let's classify the type of organic reaction in general. based on the mechanism of the reaction. Remember, mechanism is an important keyword for organic reactions. So organic reactions can happen in a stepwise manner, meaning that this reaction from the starting material A to go to B, it goes through several steps, and we call those intermediate steps, and they would have intermediate products with them. Remember, during the organic reaction, whether it's stepwise or concerted, energy should be also considered. Of course, energy would be added to the system, and energy also can be released as a result of a reaction. So, starting material A reacts with some reactant, let's say C, goes to an intermediate species. That intermediate species, very unstable, goes to a more stable final product, B. So this is a stepwise reaction. When we say a single step or concerted reaction, the starting materials are converted into products in a single step. So there are no intermediates from going starting material A to products B. This type of reactions are called concerted reactions. So what it means is bond making and bond breaking happens at the same time. During organic reactions or any kind of reactions, two things that could happen are bond breaking, and new bonds are made, bond making. So in a concerted reaction, the bond breaking and bond making happens simultaneously. Here, the starting material bond might break. It would associate with some other activated complex, transform itself to intermediate. That intermediate is unstable, as I said, it's high energy, goes to a final product B. So bond breaking and bond making are not simultaneous in a stepwise reaction mechanism. So these are the mechanism of the reaction, either stepwise mechanism or concerted mechanism. So these are the mechanisms of the reaction. They can be stepwise or concerted. In a concerted reaction, bond making and bond breaking happen simultaneously. And in a stepwise mechanism, a starting material goes to some type of intermediate step or intermediate product. That intermediate product is a high energy species. That intermediate finally goes to, when it reaches to equilibrium, it goes to products. So in any reaction also, you should remember there is an equilibrium that would be established between the product and the starting material. So that equilibrium based on the energetics would be favored either forward or backward. So in a chemical reaction, this arrow means, this double arrow is equilibrium. So this is when the reaction reaches to an equilibrium. It can go both ways. So it means that the forward product making rate of a reaction and the backward, when they're equal, at that point equilibrium would be established. For example, going from A to B, the equilibrium constant is, or the reaction would be equilibrium constant B at equilibrium, and starting material A. So this is the ratio of the two to give you equilibrium constant. The reaction is designated with a double arrow. A double arrow is an equilibrium. So we always have different arrows, so you need to be careful what arrows you are using in a reaction. So organic reaction has mechanisms. You should remember what kind of mechanism is involved in that particular type of reaction, whether it's stepwise or concerted. Most of the organic reactions happen in a stepwise, but there are some few known chemical reaction, organic reactions, where bond making and bond breaking happen at the same time. Those type of reactions are called concerted reactions, where the starting material is converted to a final product in a single step. It has only one step. This stepwise one have more than one, multiple steps to achieve the product. So in the next few slides, I will show you what kind of bond breaking and what kind of bond making happen in the stepwise reaction. Let's see what bond cleavage is. That's when a bond is being broken, and that bond cleavage in most cases needs addition of energy. That means added, not energy release. Sometimes in order to break a bond cleavage to happen, you need to put energy. So the type of cleavage that happens between two bonds, AB is a bond, would be either homolysis or it could be heterolysis. So in a homolysis, the bond breaks at halfway, meaning that the electrons are moved, the shared electrons, the covalent bond is being broken by having one electron to this and one electron to that, to B. This is homolysis. That means the shared electrons are also shared equally by the bond, the two counter atoms. The result from that reaction of a homolysis bond cleavage. A homolysis bond cleavage is a breaking of a single bond exactly in two parts. That means one single electron would be going to A, this fishhook symbol, and this fishhook symbol, half electron, shows you a movement of one electron. This is one electron movement. I'll show you some arrows here. This kind of arrow shows you equilibrium. This single arrow shows you reaction. This double arrow shows you resonance. So don't confuse the different arrows we use in a chemical reaction. So whenever you see this single fish hook, it is a one electron movement to that direction and to that atom. The result of this reaction, homolysis bond cleavage, would result in A dot, that one electron from the bond, plus B dot. The bond is totally broken. To generate, we always call the single electron species on them free radicals. Remember, now we are introducing new terminology. These are free radicals. Free radicals. Free radicals are a result of a bond hemolysis. When a bond, a single bond, an sp3 sigma bond breaks, you would result in this species. These are very reactive, very unstable. They could be an intermediate of a certain reaction, but that's the result of a bond hemolysis, shared electrons equally. When we say heterolysis, it is either to this or based on whichever is comfortable acquiring electrons, is carrying both electrons. For example, if we take A is more electronegative, when we do this, now it's not a fish hook, a single fish hook, now a double arrow. This is two electron movements. So if you have arrow like this, two electron movement. So the bond totally breaks. The AB bond breaks by a heterolysis where both of the bonding electrons, the sigma bond electrons, reside on one of the species. So that kind of bond cleavage or bond dissociation is called a heterolysis process, where two electrons are on A and B remains without any electron. That results a hole. This is electron, that's a hole. When it's a hole, when it's losing, it will be just a positive charge. So homolysis produces free radicals. Heterolysis results in cationic species, cationic and anionic species. These are also very unstable. They would recombine with something and give results. So these are highly reactive species, but I'm just showing you here how a bond breaks in homolysis or heterolysis. Heterolysis results in a positive and negative charge, while homolysis results in free radicals, equally shared one electron. So in a real example here, for example, if this undergoes a hemolysis would give you this carbon, and Z is some other species. It could be chloride, bromide, any other heteroatom. So, for example, if this is a homolysis, let's start with homolysis, you would have C radical plus Z radical. This is example of homolysis, where a carbon is just have a carbon radical, and if it undergoes heterolysis, a carbon, in most cases if it is a plus and Z is a minus with two electrons, we call this is a carbon radical, you are forming a radical. Here you are forming a carbocation. Remember now this wording. Don't be, this is a carbocation. Very unstable species formed as a result of heterolysis. You can also form, if both electrons are taken to Z, you can also form a carbonyl. Two electrons, negative charge, plus a Z, a hole. In this case, this carbon is called a carbonyl. Carbonyl. It's a nucleophile. This is a carbocation. This is electrophile. This is a nucleophile. So now we are starting to build our terminologies. A carbocation is an electrophile. It wants to capture electrons. It's an electrophile. It likes to have electrons now because it's highly positively charged. Here, this species is a carbocation, so it's a nucleophile. Nucleophile. So now, this is where we should be starting understanding how bond breaks, what kind of species is being formed, is important in understanding reaction mechanisms. So as a review, homolysis gives you free radicals. It's an equal separation of single electron movement. Heterolysis is a two electron movement. It could be either this way, where A carries all of the electrons, or it could be the other way, where B carries all of the electrons. So as an example, homolysis always makes a free radical. So the carbon radical is giving you free radicals. Here the positive carbon species. Now we are dealing organic reactions, so this is a very common encounter you will have in all of this course. Whenever you have three species instead of four that were substituted carbon, is as a result of bond cleavage, when it has a positive charge on it, where all of the electrons are taken away by the substituent, you form a very highly reactive species called carbocation. The carbocation is obviously electrophile, meaning that it loves to get somewhere electrons to be neutralized. Here you have bond breakage of this type, when the two electrons are all carried by carbon, and Z is a counter ion. We are focused on the carbon, so this is a carbanion, a carbon negative charge. Carbanion is the terminology you should remember now. We have carbon radical, a carbocation, a carbanion. Carbocation is a plus charge which lacks electron deficient species, very reactive. A carbanion is electron rich, very strong nucleophile, meaning that it needs to go to attack a nucleophile, meaning attack any positive charge species. So make sure that you review and understand all of the different terminologies as a result of bond cleavage. Obviously, these are the arrows you should be familiar with by now. A one electron movement results in free radicals. A two arrow, double arrow, shows you equilibrium between two reactive and starting materials. This just tells you a reaction in one direction. This is not a reaction. Resonance structure, when we show a resonance structure with a double arrow like that, it doesn't mean a chemical reaction. Resonance is not a chemical reaction. So be careful. This is not part of a chemical reaction. Resonance doesn't involve chemical reaction. It is the same species of electron movement, and we draw different resonance structure. Here, when we show a double arrow by a Fisher type, this is a two electron movement. It results different species based on what arrows you used. So here, the arrows, the appropriate arrow to come to this is a single fish hook. Here, both electrons are carried by Z, the substituent, not carbon. So both electrons are moved and the bond is broken. Here, both electrons, the ones in the covalent bond, are broken and carried by carbon. So these are the different arrow movements you would encounter during bond cleavage and bond making. So we'll continue with the type of organic reaction, a general summary of organic reaction. We'll just discuss about bond dissociation energy. Bond dissociation energy is the energy that is required to break a single bond. Like here, if you have a bond, which is a sigma bond, a single bond, being broken by process of hemolysis to generate AB, that's equally shared free radicals, that energy is called bond dissociation energy, or equals enthalpy of that reaction. This is a reaction by this arrow, and the bond dissociation energy is measured kilojoule per each mole. 1 mole of that is enthalpy of that reaction. The enthalpy of a reaction involves, that means the energy that's put to break the bond is the bond dissociation energy. You need that much energy to break a bond. That is called enthalpy of that reaction. So it's usually represented as delta H, enthalpy of the reaction. So let's take hydrogen gas. Hydrogen is a single HH bond, hydrogen gas. If you want to split hydrogen, you need to put energy to convert it into hydrogen radical, to H dots, or HH broken to two radicals, H radical and H radical. Obviously, to break a hydrogen bond is to put a lot of energy. So when it's being broken, you have to put that much energy. So the delta H, or the bond dissociation energy per 1 mole of hydrogen gas to convert it into two radicals, H radical, is 435 kilojoules per mole. So this value is positive. When you have a bond dissociation energy, or the enthalpy of a reaction, which is greater than 0, delta H greater than 0, as here, that reaction is endothermic. Endothermic reaction is a reaction that requires energy. You have to put energy. It's a positive sign, meaning that you need 435 kilojoules per mole to effect that kind of reaction. But some reactions, the overall reaction, if it is less than 0, that kind of reaction actually is exothermic, meaning that the reaction actually produces heat, produces energy. So this one absorbs energy. It needs energy. Most bond dissociation energies, almost all of them, they require energy. That means they are endothermic processes. So bond dissociation energy is the energy that is required to homolyze a bond. That means you have to put that much energy for hydrogen breaking, hydrogen-hydrogen bond, single bond. You have to have 435 kilojoules per mole. But it is also common some overall reactions would generate heat. That means actually they produce a innate amount of energy. Such reactions are exothermic reactions. So exothermic, endothermic, based on the delta H value. The bond dissociation energy, in most cases, bond dissociation energies are energy required to break a single bond. Therefore, they are endothermic. That means you have to put that much energy to break a bond. So these are mostly tabulated. You will find them as a tabulated data, because it has been studied how much bond dissociation energy you need to have for a certain kind of bond. Here I have example of, this is fluoromethane, chloromethane, bromomethane, iodomethane. These are all alkane compounds, substituted alkanes. The simplest alkane, you remember, is methane. when it is H is a CH4, but here we have a substituted alkane called fluoromethane, chloromethane, bromomethane, and iodomethane. So they have their respective bond dissociation energy. The bond dissociation energy, as you go down, is decreasing. That means it is easier to break iodomethane, the iodomethane carbon iodine. So here's the broken bond is the iodo. This is the bond. It's easier to hemolyze the carbon iodine, the carbon iodine bond, than to break a carbon fluorine bond, because this one requires 456 kilojoule per each mole, but here the carbon iodine bond is weaker, relatively speaking, weaker than the carbon fluorine bond. The carbon fluorine bond is very strong. It requires 456 kilojoules per mole. Next would be the carbon chlorine bond. Carbon chlorine bond, that's what is hemolyzed. Here the carbon bromine bond is what's being broken. So it's generating a carbon radical and a fluorine radical. Which one is the easiest is the carbon iodine bond. So if you have CH3I, when it undergoes bond dissociation by a homolysis, you would have CH3 radical plus I radical. This process is much easier than doing for fluoromethane. So this requires only 234 kilojoules per mole. Still, it's positive, meaning that you have to put that much energy, but this one needs much more energy than the carbon iodine bond. So it's much easier if in exam or anything like that, if you are asked which one has the lowest bond dissociation energy, carbon iodine is. There are reasons why that is easier to break. Iodine is large, so it is easy to break. Fluorine is very electronegative, highly attached to the carbon. The carbon fluorine bond is very strong. That's why it requires a higher amount of energy. So these are the kind of things you need. You don't need to memorize, but rationalize based on numbers. Here we rationalize carbon fluorine bond is very strong. Here carbon iodine is less strong than the others. Here CBr, carbon bromine bond, is the next weaker one. Then it goes up. So the strength of the carbon Z bond, Z when it represents fluorine, chlorine, bromine ion, the bond dissociation energy increases up. From in the periodic table going down, bond dissociation energy decreases, but going up for this series it increases. Bond dissociation energy is much greater than 0. For obviously it's 456 kilojoules per mole. So these are the kind of if you are given, obviously you will be given some kind of numbers, tables, but it is up to you to explain why that would be. So the carbon fluorine bond is very strong. Fluorine is highly electronegative, therefore it's highly attached to the carbon. That is a very strong sigma bond than a carbon iodine, fluffy iodine, which is easily polarizable, larger in size, easy to break. So bond dissociation energy can be a plus or a minus overall. Delta H is what we measure it with. Delta H greater than 0 means endothermic, positive value. You have to put energy, and delta H less than 0, and in a reaction mean that it's an exothermic reaction. Overall, that reaction would produces heat as part of the product. So we'll continue with the different type of organic reactions and demonstrate how the bond dissociation energy is calculated for an actual organic. Continue our discussion on bond dissociation energy. So for an overall reaction, the overall delta H, or enthalpy of a reaction, is calculated from a table of values for delta H for bonds that are broken plus delta H of bonds that are made. So delta H bond breaking plus delta H of making would give us the overall reaction delta H. That means there are bonds that are being made and there are bonds that are being broken. So we are going to calculate the delta H overall, for example, for this reaction to produce these products. So the question here is, what is the delta H value of everything that's from starting materials? We are running a reaction to make these products. So according to the formula, we need to have adding all bonds that are broken and add those are being made. So as I told you, as a convention, bonds being broken are always positive. So the values here, the bond dissociation energy values, are for dissociation. That means all are positive. So if that particular bond is being made, we take the negative of that. So bond making is a negative value. So let me demonstrate this for you by taking this tertiary butyl chloride, reacting it, dissolving it in water to give tertiary butanol and hydrochloric acid. So first of all, when I say tertiary, this chloro substituent is on a carbon that is attached to 3 different carbons. So this carbon is a tertiary carbon because it matters in the bond dissociation whether that carbon is containing the chloride or it is on a secondary carbon, is different values. So as this is a tertiary butyl chloride, I would say tert butyl chloride. So the carbon is a tertiary. So we are dealing with bond breaking because that's where the OH is replaced. So this is a bond that's being broken. So let me rewrite that. CH3, 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 Cl. This is the bond we are looking at being broken here, because here is the change. As you see, here is changed. The CO bond is made. So bond broken, one of the bonds that's broken is carbon Cl bond. In this case, here HCl is being formed. So one of this hydrogen has been broken to connect with this chloride. So one of the bonds, HOH, this is a bond that's broken. So it is OH. These are bond being broken. Here, when you see here in the product side, you have a carbon-oxygen bond being made. So what we have is CH3, CH3, CH3. This is a bond, a new bond that's formed between carbon and oxygen. So made, I'll just put made carbon oxygen, newly made a tertiary carbon oxygen. Remember where it is, it's on a tertiary carbon. This carbon is tertiary carbon. We call it tertiary because there is value for secondary as well. So here we have H and Cl is being made. So it is hydrogen and Cl. So now we have broken ones and made ones. So let's just add up everything that's broken. A carbon-chlorine bond, which is broken, that means you have to put energy into the system. So you don't take this one. Even though it's carbon-chlorine here, this is secondary one. So be careful what kind of carbon we are dealing with. This is what matches to this one. So this is a tertiary carbon. The total energy is 331. So delta H overall is calculated as bond broken. One is 331 kilojoules per mole. Another bond broken in water is the oxygen-hydrogen bond, which is this one. Oxygen, hydrogen. You get these values from tables. 498. So these are all bond broken. Plus bonds that are made are carbon oxygen is made. So the carbon oxygen made is this value. Carbon oxygen for butanol is 401. But since this is a dissociation energy, the bond made is minus 401. So it is minus 401 negative kilojoules per mole. Plus, so a newly made bond is hydrogen chloride, HCl. HCl is 431 for dissociation. For being made is negative 431. So it is minus 431 kilojoules per mole. So when you add up everything, you would get 829 is for 829 is a positive value for bonds that are broken, and the bond made is minus 832. So overall we have 3 kilojoules per mole as negative. So the net enthalpy delta H is negative 3 kilojoules per mole. This tells us the reaction is exothermic by minus 3 kilojoules per mole. So it's slightly exothermic. So because the final delta H from this bond making and breaking gives you a negative value. So the delta H overall in our reaction, in this particular reaction, is exothermic, because this is heat is finally released. Even though in some steps heat was absorbed, but the amount of heat that was released is more than the amount that's needed to make the bond. Therefore, this reaction is an exothermic reaction, going from tertiary butyl chloride to tertiary alcohol, butanol, is an exothermic reaction to form tertiary butanol and hydrochloric acid. So this is how you would be using bond dissociation energy to calculate enthalpy of the overall reaction. So we'll do more problems in another video how to apply this calculation for getting enthalpy of a certain. Continuing our discussion on the types of organic reactions in broadly classified as substitution, elimination, addition reactions are mostly what we encounter in organic chemistry. So a substitution reaction involves a breaking of a sigma bond and making of another sigma bond. So substitution reaction is usually involves breaking of a sigma bond and substituting by another sigma bond, but the organic functionality group would be transformed from one form to the other. So if I just put one organic example, so this is sigma bond making and breaking. This involves a sigma bond making and breaking. So for example, one example would be if you have metal iodide plus a chloride anion. This is electron rich, so you have a substitution of the iodine by chloride. So this is a product you will get, that is plus iodine minus. Here what you see is the breaking of the carbon iodine bond and the making of carbon chloride bond. So if I just write it like this, these are hydrogens, and this is iodine. This bond is being broken to substitute with another anion, which is the chloride anion. So this is what is being broken, and here you make CH3, hydrogen, and a new bond, sigma bond, still is being formed. So this is a bond which is being formed through a substitution of the iodine with a chloride. So this involves just a breaking of a sigma bond and a making of still the same sigma bond but with a different group. That's a substitution reaction. For elimination reaction, it's characterized by when you eliminate a group out of a certain organic molecule. Elimination always forms a pi bond formation. This makes a pi bond formation. Remember, the sigma bond making and breaking is in a substitution reaction. No new bond is created, but here in the elimination reaction, you are creating a new bond. That is, for example, if you have, in this case, you'd be breaking two sigma bonds to make one pi bond. For example, if you have C, like this, let's say these are X and Y, that to be eliminated out of the system. So if we just break this bond and that breaks that bond during elimination, you would form an alkene, for example. So these are the carbons. So what happens is you are just breaking this bond. Maybe it's a single electron transfer, a single bond to make a double bond. While a new bond is being made, this would leave. So you are forming one pi bond is being formed. So that's elimination reaction. So if you see several kind of organic molecules, and if you understand what the functional group in that compound is, you would kind of understand how it's made. For example, an alkene can be made from an elimination of a neutral molecule. So XY is eliminated. So one pi bond is formed plus XY is eliminated. So by elimination of XY from this, you are forming a pi bond. This is a pi bond. So here you see one sigma and one pi bond to make the double bond, one pi. Double bond. Double bonds are results of a pi bond. So here across the carbon-carbon bond, which is already existing sigma bond, which is this one, now you are adding one more pi. So this is a pi, this is the sigma bond. So in the next one, the other reaction we see would be an elimination addition reaction. So if you have a system like this, you always have, during addition reaction, you reform sigma bond, because you will be adding across the double bond. So the double bond wouldn't stay. For example, if I am adding ZY atoms, the product would be ZY. So these are the addition products. So you are forming sigma bond. The next is sigma bond is formed. So the alkene disappears, the pi bond disappears, because you are adding two groups here. Carbon cannot be bonded more than 4 atoms, so you have to break that bond. So the pi bond is being broken, the sigma bond still stays there. One sigma, one pi here, but always you can add over a pi bond. You cannot add over a sigma bond. If you force to add over a sigma bond, you are basically trying to break it. So the only thing a sigma bond can undergo is a substitution reaction. An elimination reaction results in a double bond. And a pi bond reacts by adding groups into itself. So these are mainly the reactions that you would see in organic molecules. They are not too many. It's just a matter of understanding few of the reaction very well, what happens during that reaction. You can summarize to most organic molecules how they are made. Either it could be a substitution reaction, it could be an elimination reaction, and it is an addition reaction. And you need to always understand substitution is the forming of another sigma bond. Elimination is a formation of a new pi bond. An addition reaction is a destruction of the pi bond to go to a sigma bond. So I will be adding more examples to this to show you particular substrates and examples of each type. So the reactions you encounter are not so many. It's a matter of just understanding few of the reaction mechanisms, and it shouldn't be overwhelming for you to understand organic reactions when you see in a molecule. So for example, here I would just show you this example. You have a pi bond system, and if the product is this, what kind of reaction is this? This is basically you have added bromine 2 into the cyclohexene compound. This is an alkene. This is an alkene compound. It's called cyclohexene because the double bond hexene. So the only thing that happened is an addition reaction. Addition reaction. Okay. Now, if you have this, and under certain condition, usually we use light to effect such kind of reaction. And if you just see here, this product, what kind of reaction happened in this? What's the reactions that happen when you see here you have cyclohexane with 12 hydrogens, you have bromine 2 as a reactant, and you are using light to effect the reaction. Such a reaction goes with light, and you have a bromocyclohexane compound. Bromocyclohexane. So what happens is you have 12 hydrogens, as I said. You have 12 hydrogens. Remember, that's what we have. But one of the hydrogen is replaced by bromine right there. So there is hydrogen here. This is a substitution reaction. Substitution reaction. So that's an example of a substitution reaction. So you have addition, substitution, and I want to show you an elimination reaction, for example. If you have this, and if you have iodine here, then in the presence of a strong base, let's say base, that's a reagent to effect this reaction, and you could be forming this plus HI. So I'm forming a new pi bond over there. So this is elimination of an H and an I group. They go to as HI, neutral molecule. This is released out of the system. So this is elimination reaction. You are eliminating in a group. Okay. So again, as a review, an addition reaction forms in a sigma bond. This is sigma bond. As this is a substitution reaction, still it just forms a new sigma bond. New sigma bond. And here an elimination reaction forms a pi bond. This is a pi bond. So you had sigma bond previously, but out of the elimination you are forming a new cyclohexene compound, which is an elimination product. And furthermore, I just want to give you one more reaction. If you have this, and if you are reacting it with water, boiled with water, and if somebody shows you this product right here, so what happened here? You have, this is a H10 compound, I would say. One hydrogen here, one hydrogen. There are two here. There are two. There are two here. 2, 4, 6, 8, 10. This is C6H10. You have an alkene, a pi bond, a sigma bond. You are reacting it with water, so you have added one hydrogen and one OH. That's what happened here. So basically you have added, this is two hydrogen now, there is OH over there. So this is an addition of water. This is addition reaction. Addition reaction. You always can add over an alkene or a pi bond system. You cannot add over a sigma bond. Addition reaction happens only if you have a pi bond system. Substitution is a characteristics of a sigma bond. Elimination is a characteristics of a group where you have a sigma bond to give an alkene. This is just a broad overview or introduction to many different reactions that we will be doing in the future. So I will next time I will present to you some exercises involving what we have covered in this video, and also continue over energy diagrams, in transition state and transition intermediates.